Good afternoon, everyone, and welcome to today's Algorithms and Data Structures lecture. Last week, we discussed maps and hash tables, and today we have one more chapter on selected topics. And selected topics is a huge chapter with all sorts of algorithms, and we will not be discussing all of them, only some, and obviously only the ones discussed are relevant to the coursework or the exam, not the other ones. And every year I try to add more algorithms to have some selection of what I'm teaching towards the end in the term. And we will start with the fast matrix multiplication. And then we will also do the fast inverse square root. And we'll briefly talk about the others, but just a high level, just what it's about, but we'll not discuss those topics in detail. And matrix multiplications are something you learn in your first semester on linear algebra, or you have learned this in school. And it turns out matrix multiplications are super important in mathematics, but also in computer science and artificial intelligence. For example, we can use matrix multiplications for matrix inversion. We can compute the determinant from a matrix efficiently by using matrix multiplication. We can solve linear systems and so forth. But you can also use matrix multiplication for training neural networks, for example. You can use matrix multiplications for computer graphics and lots of other problems. So matrix multiplications are super important. And we will quickly draw something on the iPad, because you all should be familiar with how matrix multiplications work. And you have a matrix A and a matrix B, and in order to multiply them, there's a very nice visualization how to do this. So for example, we have our matrix A and our matrix B. So this is matrix A and this is B. And what we want to have is A times B. And we have it's 2 by 2 matrices for now. So we have elements A11, A12, A21, and A22. And here we have elements B11, B12, B21, and B22. And we want to calculate our matrix. And for this first element here, in order to calculate it, we multiply A11 times B11, so something like this, and we add then the product of A12 and B21. Are you all familiar or proficient with matrix multiplications? Maybe thumbs up or thumbs down. Certainly something you should be fine with. And like this, you can calculate the other 4 entries anyway. But since you have learned this, we don't need to revise this. Now, we can think about the complexity of matrix multiplication. And concretely, we can say that A is a matrix that has M many rows, P many columns, and we can only multiply this with B if B has P, if B has P many rows, and then B can have N many columns. So this P must be the same. So P many columns in A and P many rows in B. So that dimension needs to be the same for both, that we can actually multiply them, and then M and N is something we can vary. If we want to know the complexity of matrix multiplication, then this is O of M times N times P, or we can just say that M times P times N, and it's in the right order. So this is the O complexity, because I need to go through the M many rows, the P many columns, and from the other matrix then the P many rows and the N many columns. So this is O of M times P times N. Now, if I say they're, say, all the same, or I just care for the largest dimension, then we just say the matrix multiplication is O of N to the third. This is the naive matrix multiplication, and obviously we can do this for matrices that are much larger than just 2 times 2 matrices. And now we are wondering if we are able to do matrix multiplication faster. Who of you, maybe without looking at the slides, does any one of you see an obvious way of how we can speed up matrix multiplication? If you see an obvious way, maybe thumbs up. If you don't see an obvious way, thumbs down. Just want to see if this looks trivial for anyone, if we can have something that is better than O of N to the third. So there is someone who sees something trivial. Maybe you want to share with us. So one student says, skip the rows or columns with only zeros. Yeah, maybe that could be a minor hack in some cases, but it doesn't necessarily improve the complexity. And we want something that actually improves the complexity. And in order to do this, we will quickly go back to the slides, because what I want to show to you is well formatted in the slides. And we will now look at the Strassen algorithm. It's an algorithm named after Volker Strassen. We will later see how it actually leads to an improved complexity of the matrix multiplication. And concretely, we have, for now, we only assume we have square matrices. And what's also important is the square matrices A and B. They must be of type 2 to the n times 2 to the n, so 2 to the n many rows and 2 to the n many columns. So A and B must have the same size. And if your matrices do not have this size, you need to make them bigger, and you just fill up the remaining spots with zeros. So that's important. But for now, we just assume they are of dimensions 2 to the n times 2 to the n. We only care about real numbers here. So we say A and B that we multiply, and then obviously C, which is the product of A and B, they are of dimensions 2 to the n times 2 to the n. We deal with real numbers. And we want to calculate this product, so of A times B. And we have just tried on one small example, so 2 times 2 matrices, how to calculate this product. And we will try to split these matrices into block matrices. So A and B could be relatively large matrices, and we will now split A and B each into 4 equally sized block matrices. So A11 is the upper left quarter, A12 is the upper right quarter, and so forth. So we split A, which is a very large matrix, into 4 equally sized blocks, and we do the same for B. That's why I'm also showing you this on the slides, because this is still bold. So we use a bold notation for a matrix A and in uppercase, and we have an A is still an uppercase and bold, so a capital bold. That means it's still a matrix, because before on my slides, I used a lowercase character, which was not bold, that was a scalar value, but here this is still a matrix. So A11 is a block matrix. And our result C that we want to calculate is eventually also now built, or is also a block matrix of 4 equally sized blocks. And now we are wondering, what is this useful for? And it will take us a little bit to actually make it to the improved complexity. And we will write this out now on the iPad. So I will just write this down for you again, and then we will see what these block matrices are actually useful for. So here we say block matrices, and A, because on the iPad I'm hardly able to write A in bold. So this is just now in bold. That's why I've shown you this in the slides before. So A11, A12, A21, and A22. But remember, it's always in bold. And for our matrix B, we're doing the same. So B11, B12, B21, and B22. And our result C, that is the product of A and B, we also write C11, C12, C21, and C22. Remember, they're all in bold. And now I want to know, how can I actually, so these are all blocks. Sometimes you find for such block matrices also a notation that is sometimes splits this matrix into such blocks. This is something you would sometimes see in a different notation. And I want to know, how can I calculate this block C11? And it's exactly what I have done before. It's the same procedure, how I can calculate this block, but yet we will write it out once. So C11 will be a sum of 2 products. So it's A11 times B11 plus A12 times B21. And we could be doing this now for C12, C21, and C22 as well. You can very easily do this on your own if you wish. You will also see the solution in the slides. But something, and we will look at it in a moment that it's there, but what we see is we have one multiplication here, we have one here, we will have one here again. I'm just putting where we have the multiplications of the block matrices. So we will have, in sum, we will have still 8 multiplications. So, and we have these pluses, but the pluses don't matter for now. We only care about the multiplication. So switching to this block approach, that we have a very big matrix and we split it into blocks, and then we try to do this calculation with blocks. That means we still actually, we're not dealing with concrete numbers yet, but within these blocks, we again need to split them again into smaller blocks and smaller blocks recursively until we have scalar values that we can finally multiply and add. So what I've shown you here is just a top view. Actually, it's a recursive view. We need to dig deeper because this block here, so C11, is something you can again split into 4 equally sized blocks recursively. And that's why we said that A and B and C, we've said this before, A, B, and C, they need to be of dimensions 2 to the n times 2 to the n. And because this is the case, we can recursively split these blocks into smaller and smaller equally sized blocks until we deal with scalars. So far, this recursive approach to have a large matrix and split it into blocks rather than dealing with all the scalars directly doesn't lead to any improvement in terms of complexity. But it will very soon. And what I had just shown you was this calculation of C11, which is A11 times B11 plus A12 times B21. And these remaining 3 ones I had not written out, but I had shown you in total, it's still 8 multiplications. Now, we want to calculate this here using less multiplications. Do you think this is possible to calculate these 4 C's with less multiplications? If you think this is easily possible, thumbs up. If you don't see how to do this, maybe thumbs down. And no special cases like zeros or whatever, just in general. And it's probably none of us can see that easy because it isn't that easy. And it turns out you can calculate this here with less multiplications by introducing auxiliary variables. You can introduce 7 auxiliary matrices. I'm not deriving this for you. It took Mr. Strassen quite a while to derive this on his own decades ago. And what he derived are 7 helper matrices. And what I noticed for each helper matrix, I only have 1 multiplication. I have a multiplication here, there, here, there, and so forth. I may have more additions or subtractions, but I have less multiplications for now. I only have 7 multiplications to create these auxiliary matrices. My goal was actually but to compute these C's, not these auxiliary ones, but for the auxiliary ones, I only have 7 multiplications. And then I can use additions and multiplications of these auxiliary ones to calculate my C11 to C22. So I introduce more multiplications and additions, but I have less multiplications. And multiplications are the expensive part of matrices, because if you add 2 matrices, adding 2 matrices is O of n squared, because I just need to go through both matrices at the same time. So it's O of n squared. I look at the first element of 2 matrices, then the next element, and I just add them together, or I subtract them, whatever. So multiplications are far more expensive than additions of matrices. And the Strassen algorithm re-expresses these 4 C's by adding and subtracting these auxiliary matrices and calculating the auxiliary matrices. I need to introduce additions, but I have less multiplications. I only have 7 multiplications, not 8. Feel free to try on your own if this is correct. You can obviously try to calculate this here on your own and test if C11 to C22 are correctly calculated. And you need these auxiliary matrices and finally add this here together. This is something I had sometimes put in some exams in the past as a sub-problem. So in some of the past problems, in some of the past exams, I had a big problem on the Strassen algorithm. And then maybe one tiny sub-problem was to show whether C11 is calculated correctly, and you need to show this. But you just plug in the auxiliary matrices and simplify the term, and eventually C11 has to look something like this. And if you try this, you will notice it's correct. So the Strassen algorithm works, and it's important it does this recursively because just the block matrices alone are not enough, because you still need to break your block matrices into smaller block matrices until you have scalar values. So it's a recursive procedure. As before, when I had introduced this block notation, I also said it's recursive, but this time using these auxiliary matrices, we can actually do this computation cheaper. And now you're wondering, what does cheaper mean? We are introducing more lower order terms because additions and subtractions of matrices are lower order terms. So this adds more lower order terms, but we have less multiplications. And remember, it's a recursive procedure. And so this will definitely lead to far less multiplications in total. And now you're wondering, what's the impact? The impact is the Strassen algorithm has a complexity that is O of n to the binary logarithm of 7. So we have 7 multiplications, and we deal with the binary logarithm because we split a matrix into a 2 times 2 block matrix. So this is that binary logarithm. Had we split them in a different way, maybe a different logarithm, and then we have 7 multiplications rather than 8. And this actually leads to an improvement. If we use the regular naive matrix multiplication, say on these blocks we had first done without the auxiliary ones, then this would be n to the binary logarithm of 8, which is 3. So O of n to the third. And O of n to the 2.8074 approximately is a better complexity class. Do you feel this is a substantial improvement to n to the third or not? Maybe thumbs up if you think it's a substantial improvement, thumbs down if you don't think so. So maybe some more votes. There's a well, we are somehow evenly split, or now there's even a majority for it's not substantial. We will later see if it's substantial or not, but first of all, it's a better complexity. But it adds more lower order terms. Because of these larger lower order terms or large constant, this is something you would only do for matrices typically where you have more than 100 rows or columns. So for tiny matrices, you would not be running the Strassen algorithm. And if you look at like professional implementations of matrix or linear algebra libraries, then what you will often see is that they only use the Strassen algorithm or some other fast matrix multiplication algorithm if you have like more than 100 rows or columns, because then for larger n's, it actually starts to pay off. For very small n's, it actually takes longer. But we learned this about the O complexity. It's for large n's, so asymptotically. The Strassen algorithm comes with one drawback. The numerical stability is reduced. Numerical stability here comes into play if you deal like with real or like float values. With integers, it doesn't make a difference. But if you deal with float values, your result accuracy may be slightly diminished because you have more and more operations. And if you with float values, you have some loss of precision at a certain degree, and this could slightly diminish your result accuracy. But this is something also maybe not to be worried about in this course. Now, this is the Strassen algorithm. And now you're wondering, can we even do better than O of n to the 2.8? And is this actually substantial? Well, the Strassen algorithm is a substantial improvement over the naive matrix multiplications. If you make n very large, for example, in machine learning applications where you deal with huge matrices, then n to the 2.8 leads to a significant improvement compared to n to the third, not really for super small matrices, but for very large ones. This is certainly something done. And this is something you would be doing if you professionally implement matrix multiplication, or if you use matrix multiplication, say, to train a neural net. The libraries in the background, they will use a fast matrix multiplication algorithm like the Strassen algorithm or some other fast matrix multiplication algorithm. And now we can wonder, are there better ones? Can we do better than 2.8? And in fact, over the years, more and more fast matrix multiplication algorithms have been proposed, and there are. So the naive matrix multiplication is O of n to the third, and then Strassen proposed his algorithm in the late 60s with 2.8 something, and this actually led to more and more papers improving matrix multiplication down to under 2.4, so 2.3 or 2.33, whatever. So there are improvements, but it turns out that essentially everything that came after Strassen is only purely theoretical. That these improvements, yes, they lead to a better n or to a better complexity, but only for super huge matrices that are too big to fit in nowadays computers. So something like this stuff down here, yes, it's better than Strassen, but we just don't have such large matrices that fit in our computer that this would actually lead to an improved running time. So for everything practical, the Strassen algorithm is actually the quasi best we can use. This is something I presented like this in this lecture until 2 years ago. 2 years ago, the lecture stopped here and we were done with the fast matrix multiplication. And then something happened about a year ago, or maybe a year and a half ago. And actually, a new matrix multiplication algorithm was found that is better than Strassen, not as good as the other ones, but better than Strassen, and is actually usable on nowadays matrices we are using. So the lower order terms added are not that substantial, so it actually can be used on matrices. And we'll talk about this now. So this is where the lecture ended 2 years ago, and last year it appeared, and I directly, or it maybe appeared a year and a half ago or something like this, and then I added it directly to this course. So you see, even a foundation course in algorithms and data structures is affected by advances in research. And what is super interesting is this paper that appeared. So it actually, yeah, it appeared in October 2022. So after I taught the course 2 years ago, but before I taught it 1 year ago. And this paper was published by DeepMind. DeepMind, who of you has heard about DeepMind? It's a company, maybe thumbs up, thumbs down if you ever heard about DeepMind. So some have heard. DeepMind is a subsidiary of Google, focused on artificial intelligence. They are the company that built AlphaGo, for example. So this AI that started to beat the best human Go players like 10 years ago or something like this, or 8 or 9 years ago. So that's that company. It's a subsidiary of Google. And they actually found a better fast matrix multiplication algorithm that works in practice. And they used an artificial intelligence in order to find that algorithm. So they did not manually like Strassen, because this probably took Strassen many, many days or years to come up with, to find this structure that was hidden in a matrix multiplication. But they found something, or DeepMind found a better matrix multiplication algorithm, but not by hand, but an AI actually found it. So they built an AI to do this. The AI is called AlphaTensor. What is a tensor, you may ask? So you know a vector goes along 1 dimension, a matrix goes along 2 dimensions. And a tensor goes among k many dimensions, so it's a generalization. So a vector or a matrix, they are tensors, but tensors can have more than just 2 dimensions. So you could have a matrix in 3D or in 10D, whatever. Tensors are also of use when you build complex neural networks, say complex convolutional neural networks or neural networks working on 3D data. Typically, you would be using some tensor approach. So this is what a tensor means. And the AI proposed by DeepMind is called AlphaTensor, and it's an AI that finds fast matrix multiplication algorithms. It actually builds on AlphaZero, and AlphaZero is one of the AIs that achieved superhuman performance in playing the board game of Go. The first DeepMind AI that bet the best human players on Go was called AlphaGo, and AlphaZero was the next one, an extension or an improved version. And that AI that was used to play the game of Go or learn this, it actually turned out it can be reused for many other things, or this approach. It can be used to improve a Google search, but it can also be used for AlphaTensor. We don't discuss in this algorithms and data structures course how AlphaZero works, because for this you need quite a lot of AI background, which is not the idea of this course. But we will see what AlphaZero actually delivered. And AlphaZero found multiple fast matrix multiplication algorithms. One of them worked particularly well by multiplying 4 times 4 matrices. So actually matrices that are not size 2 times 2, but 4 times 4, so a different size. And in order to do this, say in a naive way, you would need 49 scalar multiplications. So before we've seen the 2 times 2 matrices, we would need 8 scalar multiplications, was reduced. And now with these 4 times 4 matrices, in a naive way, we would need 49 scalar multiplications. But with this algorithm found by AlphaTensor, we only need 47 of those. And what you see down here is a comparison of such algorithms. So multiplying a 2 times 2 with a 2 times 2 matrix, so Mn and P, this was used using the Strassen algorithm. And I'm sorry, the 49 here is obviously not the naive one, but it's actually the Strassen algorithm. The Strassen algorithm applied not to 2 times 2, but 4 times 4 matrices. And this is exactly shown here. So Strassen, the Strassen algorithm from the first period could also be used for 4 times 4 matrices, and you would have 49 multiplications with the Strassen algorithm. The naive one would obviously be more than 49. And this new algorithm proposed by DeepMind, or which was found by AlphaTensor, for such 4 times 4 matrices only needs 47 multiplications, not 49. And for the 2 times 2 matrices, it didn't find anything better. It found a Strassen algorithm again, and I think some equivalent ones, but it didn't lead to an improvement. But for larger matrices, so splitting this huge matrix not in 2 times 2, but 4 times 4 ones, we would actually be able to do this with less multiplications. And this is 47 multiplications rather than 49. And does that lead to an improved complexity? Yes. Before I said for the Strassen algorithm, we had a log2, so a binary log of 7, because we had needed 7 multiplications, and we used 2 times 2 matrices. Now we use 4 times 4 matrices, so we need log4 of 47 multiplications. And this leads to a slightly improved complexity, because the complexity is O of n to the 2.77. And if we use the Strassen algorithm, say not for 2 times 2 matrices, but 4 times 4, so one more step in the recursion, this would be log 4 of 49, which is just the complexity from before, so the 2.8. And now we got even better. And what we got better is just tiny, but still for large n's, it runs faster. And this actually is usable in practice, which makes a huge difference compared to all these other fast matrix multiplication algorithms that were derived over the years, because they have a better complexity, but not for the data we have available. So this is something super interesting, and you can now see how even artificial intelligence impacts your introductory course to algorithms and data structures, because an AI has now allowed us to find a better matrix multiplication algorithm. We look at what the algorithm looks like in a moment. And I think this is something we're going to see more and more in the coming years in computer science, because we have a lot of heuristics and a lot of foundation algorithms that super smart people came up with 50 or 60 years ago, and others were not able to improve these heuristics further. But now with an AI, we can probably improve these heuristics. And I think this is something we're going to see more and more in the coming years with foundation algorithms that are being replaced by new foundation algorithms that were not found by humans, but by an AI. So it's a super exciting time. And many professors think that once they have created their slides for algorithms and data structures, they would never have to change them again for the rest of their career. I don't think so, because we will see more and more of this. And maybe in the future, we will see, I don't know, improved sorting algorithms. Something like this was even proposed by DeepMind, improved sorting algorithms, not for large data sets, but for super small data sets, like I think sorting 2 or 3 numbers or something. DeepMind built an AI that found an algorithm that needs less steps in assembly code in order to sort something. So stuff like this, we're going to see more and more. That one, the other one I just mentioned, did not improve the complexity, but the effective runtime. And so we're going to see more and more of this, I think, in the coming years. Now, what does the new algorithm look like? So we have 4 times 4 matrices, and we have this result here, C, which is the product of A and B. And it actually turns out that you can calculate C11 up to C44, but you need a lot of auxiliary matrices. The auxiliary matrices, they come with less multiplications. Yes, they come with 47 multiplications, not with 49, but it's certainly far more difficult to look into this than the Strassen algorithm. So you don't need to remember this by heart or to prove that it's correct. This was done by others. We don't need to do this, but we see we have far more auxiliary matrices, and it's far more complex to calculate the final blocks, but it leads to an improvement. So this is how AI is impacting matrix multiplication. And there are also some theories about how to use quantum computers for fast matrix multiplication. But this is something we won't be discussing for now, because quantum computing is something we'll discuss in the next lecture. There's a question here, why are 1,000 additions better than a few multiplications? Because I've always said we deal with blocks. We have large matrices that we split into smaller and smaller blocks. And when you add 2 matrices, so 2 blocks, then this is O of n squared, while multiplying would be O of n to the third. So we talk about large data sets, but this new algorithm proposed by DeepMind, maybe you wouldn't be using it for 100 times 100 times matrices, but maybe for 100,000 times 100,000 or some other threshold. You would need to see the paper, what a suitable threshold would be. But this is now some data you're going to deal with when you train large neural networks. And then you rather have more additions of blocks than multiplying blocks. So this is the fast matrix multiplication. There are more topics here in the slides, like how you can actually generate random numbers. This is something we're skipping, but feel free to look into the slides if you're curious how a random number generator works, at least a very simple one, because all of us use random numbers and somewhere they need to come from. This is, I think, something I discussed in a lecture last year, but this year we're not discussing this. And I still have the recording of the random number generation. So you can find this in the Nextcloud, what I discussed last year, but I think I can also add this to YouTube, and I'll try to upload this from last year, that we also have this recording of the random number generation available. Today, we're going to do a different selected algorithm. So this also helps me to have a little bit of variation. And the algorithm we're now looking at is the fast inverse square root. What's the fast inverse square root? So you have the square root of x, which is this one here. And the inverse one is you divide 1 by the square root of x. This is actually an operation you're running very often in computer programs. For example, in signal processing, just to normalize a vector, say we have a vector which has 3 entries, v1 through v3, and you want to know its length. So the length of v is just v1 squared plus v2 squared plus v3 squared, and you take the square root of the sum. And then so we had our vector v, and v normalized is you just take v and you divide it by its length. And then you have normalized this. So we're dividing by something here, and we're eventually dividing by the square root of something. You can also use the fast inverse square root, for example, in computer graphics. For example, for the angles of incidence and reflection, for lighting and shading situations. This is also something where you would often use the fast inverse square root and so forth. Now, you all know how to do this in Python. You have some number x, and you divide 1 by the square root of this. So it's an operation that looks fairly easy to implement, because you can all use the square root function from a library, from a math library. But internally, somehow, this function calculates the square root, and you don't know how. And you can easily use a library to do it, but what's actually behind the library? So how can you actually calculate the square root? We'll discuss this first. And once we have discussed this, we will see how to calculate this one here actually efficiently. So not in a slow way, but in a slightly faster way, because this operation is used so often in certain programs. So in signal processing and computer graphics. And if this is calculated all the time, say in some rendering, if we can slightly improve the running time of something like this, this could be very helpful, for example, in a video game or some signal processing application. So calculating the square root, we could create a lookup table. For example, the square root of 9 is 3, the square root of 25 is 5. So we could build a lookup table. But a lookup table may be super efficient, but I need to create lots of entries beforehand and then look it up. And maybe there are some new inputs which are not available in the lookup table, and then I don't have them. There are other approaches how to calculate a square root. For example, we can use Taylor expansion. So Taylor expansion allows us to approximate a function. Are you all familiar with the Taylor expansion, say from your Maths 1 or Maths 2? Maybe thumbs up or thumbs down if you know the Taylor expansion, or if you don't know it. So everyone seems familiar with the Taylor expansion. So we could use the Taylor expansion to approximate the square root function. And if you've done the Taylor expansion, you know how to do this, because you just need, you would take a few steps, obviously not to infinite, but some steps. You need the derivatives of the square root function and fill in the other parts, and you are more or less done. There are other approaches how you can calculate the square root. For example, you can take advantage of an exponential identity. Square root of x, you can rewrite as x to the half. And here we can use an exponential identity because we can always raise something, or we can always put something to e to the power of ln. So because e and ln are just inverse functions. So we can do that in order to rewrite this. So far, it doesn't seem to lead to an improvement, but when you have ln of x to the half, you can just move the half in front. So if we know how to calculate the e function and the ln function, we can use this now to calculate the square root function. But this does not really lead to an improved running time because somehow I need e, that's okay, and e to the power of something. And so I need a power function and I still need a logarithm function. And here I have the next problem. How do I calculate the logarithm? I can have a lookup table. I can do a Taylor expansion or something else. So I'm just turning one problem into a new one. Probably the exponential identity is nice to have, but it will not lead to an improved running time. But at least we know now how we can calculate the square root. There are lots of other algorithms or approaches of how to calculate the square root, because somehow it needs to be implemented in your library or in your calculator. And if you know how to apply the Taylor expansion, for example, to a logarithm, you could apply this here and put it in there, or you use the Taylor expansion for the square root in the first place. All of these are valid approaches, but I'll show you now another approach that is actually taken, and it's something that will look a little bit obscure, but it's something I think one should have seen, and then you know how to calculate later the fast inverse square root. Again, another question, are you all familiar with the Newton's method to find the zeros of a function? Maybe thumbs up, thumbs down if you've seen Newton's method or not, because we have not just our regular students here, but also exchange students, and maybe some more hands, because I got limited responses, but there was, and don't feel shy clicking a no, because this course is meant for you to learn something. So I'll show you this then. So actually lots of students now have not seen it, but also lots who had seen it. So it may depend on the degree program you're in, whether it's discussed in the maths 1 or 2 or not. Maybe for the ones who have seen the Newton's method, let us know in the chat where you have seen this. I didn't learn this at university. I even learned this in high school before. But those of you who had seen it, maybe just put it in the chat. I'm curious because there were lots of students now who had not seen it. So may depend on the degree program and who teaches your maths 1 and 2. So the Newton method is a numeric algorithm that finds us the zeros of a real valued function. This is also in the literature sometimes called the roots, but I rather refer now to the zeros. So where this function is 0, because we will later use the Newton method to calculate the square root function. So root would mean in this context the zeros. So I rather refer here now to the zeros in the Newton method. And the Newton method looks the following. So I have some complex function, and I'm just not able, using algebra or an analytical solution, I'm not able to get an analytical solution of my function. So where my function is 0. For simple functions, you all know how to figure out where a function is 0, but for non-trivial ones, you probably need a numerical technique. And what you do is with the Newton's method, so you want to solve this for your variable x, for which x the function is 0. And what we need is, in addition to our function f, we need its derivative f prime. And I would still be happy about your responses in the chat, because there were quite some students who had seen the Newton's method, that you let me know where you have seen it, because there were also lots of students who had not seen it. So this would certainly be helpful. So one student says he taught it himself. One student saw it in high school. Maybe it's still taught in your Maths 2 lecture in the remaining part of this term. I don't know, but we're discussing it now because we will need it. So what we do is we will start with a guess x0 where the root could be approximately, or where the 0 could be approximately. It doesn't need to be the exact one, but we just make some guess x0. And then we can try to approximate a better solution of x, which we call x1. And this is x0 minus the function of f at x0 divided by the value of the derivative at x0. And this will lead to a better approximation of this 0. So x1 is better than x0. And we can repeat this process and we can generalize it. So we can say the next x, xn plus 1, is xn minus f of xn divided by f prime of xn. And you keep doing this procedure until it more or less converges. Why does this work? There is a geometrical interpretation for this. So if I have some xn, so this is my xn, and we see this is not a 0 of the function. But if I put a tangent at this point, xn, f of xn, so this point is on xn, and the function value at xn, I try to put a tangent there, and then I check where this tangent intersects with the x-axis. Then this is actually a much better approximation of the 0 of the function. And you all know how to find the tangent of a function. And eventually what I'm doing here is I'm just going along the tangent. I intersect it with x, and I keep doing this repeatedly. And that's why I say x of n1 is, x of n plus 1 is xn minus f of xn divided by f prime x of n. There is lots of literature that derives the Newton's method, but this is not a maths course. It's an algorithm and data structures course. So it's just a helper tool for us to clue now all together for our algorithm to later find the fast inverse square root. Now, we will do the next step on the iPad. So we call this computing square root of x, Newton's method. And what I just write down as a revision, because we will need it again, is the Newton's method, because we will now apply this. So Newton's method, x of n plus 1 is x of n minus f of xn divided by f prime, which is the derivative of x of n. And now for calculating my square root, so what I want to know is for some value a, so I write this here, some value a, I want to calculate the square root of a, and this is the one I want to approximate. Later, we want 1 divided by the square root of a, because the fast inverse square root, but this will come later. First, we do this with the square root. And then we try to improve it to get the fast inverse square root. So what I want to know is for which x, when I apply the Newton method, for which x I will eventually achieve the square root of a. And you're probably wondering, how can I apply all of this now, calculating the square root to the Newton method? Because the Newton method is an approach to find the zeros of function. But here I want to find the square root value now. Well, we can try to re-express this, and we can say, so we square this, so it's x squared is a. And we can now say, well, x squared minus a is our function, f of x. And we want to know where x squared minus a is 0. And I want to find a solution for x, and that solution for x squared minus a, that will be when I apply the Newton method iteratively, this will be eventually my solution for the square root of a. This is the value I want to calculate. What I also need is, for the Newton method, is the derivative of my function. So it's 2x. And now I can just start applying this to an example. So we will always need this equation here, or this calculation, and say I want the square root of, say, the slides, I have my example, the square root of 612. And I have no idea what the square root is, but I could say my guess x0 is 10. Obviously, the square root of 612 is more than 10, because 10 squared is 100, but it's maybe not too off. And if we use the 10 now, we still have numbers that are actually fairly okay to deal with. So now I want to approximate x1. So x1 is x0 minus f of x0 divided by the derivative of f at x0. So x0 is 10, and f of x0 is, f of x is this. And so I put x0 in, and my a is the 612. Because the a was the value from which I want the square root. So f of x0, and x0 is 10. So I'm putting this in. So I have x squared, so it's 10 squared minus a, and a is the 612. And I divide by 2x, and my x0 is 10, so 2 times 10. If you use a calculator, you will get a value that is 35.6. It's obviously not the solution. And we can continue this now in order to calculate x2. And x2 will be x1 minus f of x1 divided by f prime of x1. And now we can plug this in. So x1 is this value here. So this is now 35.6 minus, we put x1 in, so it's 35.6 squared minus a, which is still 612, because this is the square root we want to get from, times 2 times 35.6. Use a calculator, you will get something like 26.39 and so forth. And you keep running this for a few more iterations, and you will actually have a very good approximation of the square root of 612. And this is something I have formatted very well in the slides, and it's this one here. So we have just done this for x1 and x2. And we keep doing this for x3, x4, x5, and we see we converge very quickly. And the underlying parts are actually the digits that are already correct. So x2 has a 2 in the front, which is correct. x3 is 24.7, which is correct, and the rest not yet, and so forth. So with each further iteration, we become very, very quickly far better and converge very quickly towards the zero. So we can see we can apply this Newton's method, not just finding the zero of a function, but we rephrased our square root problem eventually as an optimization problem for which we want to get the zero. And then we can finally use the Newton's method to calculate the square root of a number. And we see it works super well. Now we know how we can very efficiently calculate the square root. And this works far faster than, I don't know, using the exponential identity. The Taylor expansion is a totally different approach, but a Taylor expansion, you have a lot of these, you need a lot of the derivatives, higher order derivatives, and evaluating them may also become extremely slow for a function. Here, we could use probably the Taylor expansion for the Newton method. We could use the Taylor expansion for calculating the square root, but I wanted to show you the Newton method with a concrete application. It works fairly well. Now, I wanted to calculate the fast inverse square root. How do I do this? Well, I could just calculate the square root of x and divide 1 by that. How to calculate square root of x we've just seen with the Newton method. If I want the inverse one, then I just calculate 1 divided by what the Newton method gave to me. However, we can again skip that one multiplication and we could apply the Newton method directly to this one here. Just as before, we will say, I want the square root of a, which is some concrete value, 1 divided by that square root. I want to pose this as a problem for the Newton's method. So I want to find an x where this holds true. I need to reorder this equation so that a is something. And then I take, I want to make sure that the one minus the other, in this case is 1 divided by x squared minus a, is actually 0. And for this function, I want to find its root. What I need is the derivative of this function, and the derivative of such a function here is fairly easy. It's just minus 2 divided by x to the third, but feel free to try this at home. And now I have f of x and f prime of x. And with some initial guess, x0, I can use the Newton method to directly approximate this. So now we have seen a few proposals how we can actually efficiently compute the fast inverse square root. This is still, you know, regular mathematics using some numerical algorithm. But now will come the scary part. There was a video game many years ago named Quake 3. And I'm not playing, I don't have time to play video games. I think I played Quake 3 decades ago. But the source code later became public. And when software developers looked through that video game code, they found a very strange piece of code that surprisingly helps to calculate the fast inverse square root even faster. And we need the fast inverse square root a lot in video games, as we've seen before when we looked at applications. And there is a piece of code in C that eventually does the fast inverse square root. It's called R square root for reciprocal square root, or we just call it here inverse square root, but the R for the reciprocal one when we started this, we said you can also name it the reciprocal one, but we just call it the inverse square root. And what does this function do? It does some strange stuff. We have a number, and this number is assigned to y. So this code is in C, but it doesn't matter. And what it does is it takes I and does a bit shift by 1. And then it takes this strange constant and subtracts this bit shift. And you see there is a comment here that someone wrote because no one had any clue what this operation would eventually do. How can this actually, and there are a few more steps in here, because then the I is converted into float and whatever, and eventually Y is returned. There is also a first iteration for the Newton method. You could have a third iteration, whatever. But what does this do here? And this is something that you find on the internet a lot, and it confused people quite a lot. And we'll look at now what it actually does and why this approximates the fast inverse square root extremely well. No one knows how this came up. Some genius must have found out that with this operation, you can approximate the inverse square root very quickly. When we have float numbers, we somehow need to represent them in our computer. And for this, we use the IEEE 754 format. Are you all okay with this format? You should have maybe seen this in an introduction to computer science or not. Maybe thumbs up if you have ever seen how to represent a float number in a computer or not. But there are lots of thumbs up, so you've seen it. And for example, we have some number now for x, and we want to calculate its inverse square root. So for x that is 0.156, whatever, we have this solution here approximately. And if you know how to represent float numbers in the IEEE 754 format, then you can see we can actually represent it like this. It doesn't matter for now how to convert a float number into this IEEE format, but this is just our format in zeros and ones. And then we saw the next step was we took our number I and we bit shifted it by 1. So we moved all the bits by 1 to the right. So I had this bit pattern and I shifted it just by 1 position to the right. Then I have this magic number, this hexadecimal value, which can also be represented fairly easy in this format. So this is some number in the IEEE 754 format. And then we saw the next step was we took this magic number and we subtracted the bit shifted input. So, and the result is if you take this so-called magic number and you subtract the shift, you get this one here. What does that number mean? If you're familiar with this IEEE 754 format, you know the first digit has a meaning, then the next 7 digits have a meaning, and there's some way to convert this IEEE 754 format back into a float value. And eventually, these operations we had just seen before, this is our initial number in that we wanted to use. It was the 0.15 whatever. It's just this number represented from the line before or from the page before. But now we've just split it the right way for the IEEE 754 format, so we can easily convert it back. Then we have bit shifted it by 1s, which changes this number. This here was the magic number, and the magic number, and we subtract this bit shift, we get this result here. And this result is 2 times 1.307 whatever. And this is actually, so 2.6148 whatever. So 2 times this. And this is actually super close to our expected result, because the expected result is 2.52 whatever. Concretely, we are off by 3.4%, but just doing some bit shifts and some bit manipulation, we could very easily approximate the fast inverse square root. And if you look at the original code, it still does one iteration of the Newton method on top, and then it becomes even better. So this is just one iteration. A second iteration would be even better, but it would lead only to a marginal improvement, and that's why it's commented out. So I know this looks strange, and no one really knows who came up with this, who found out that this operation actually leads to a super fast calculation of the inverse square root, because stuff like this you can do super easy on your CPU. You just bit shift by 1, you subtract something, and you're done, and you're already quite good. And then you do one iteration of the Newton method, and you're even better. The fast inverse square root and where it comes from in the code in Quake 3 is explained in detail in a corresponding Wikipedia article. And I hope you found this interesting, that there are absolutely no non-conventional ways to calculate such stuff. We've seen, first of all, how to use the Newton method. We've seen other approaches, how to calculate the square root. So from now on, when you use the square root method function in a library, you have some idea of how you can actually calculate it on your own without just relying on a calculator or someone else's code. So this is the fast inverse square root. In the slides, there are more topics that I'm not explaining now in detail. Just a few words on it, but this is obviously not relevant to the exam. Prime numbers are of great interest in computer science, especially in cryptography, random number generators, error correcting codes, hashes. So this is maybe particularly interesting for the cybersecurity students among you. And the question is how can we efficiently generate new prime numbers? There are very naive ways in the slides, which are super expensive. And it turns out there are far better algorithms, including the prime number sieve or the sieve of Eratosthenes, that allows us to very efficiently generate prime numbers. But it's not relevant to the exam this year. Every year in this course, I discuss the fast matrix multiplication plus one other algorithm. Last year, I did the random number generation. This year, we've done the fast inverse square root. Maybe next year I'll do the prime numbers. We will see. There is an outlook that I briefly want to discuss. If you look at the coursework, there is the coursework problem on string matching. Concretely, this is the exam bonus. No, it's the mandatory problem, which is string matching. This is something that you can study on your own from the book and then implement these algorithms. And so we don't need to discuss this here in the course. And there are obviously lots of other very interesting selected algorithms that I wish I was able to discuss in this course. But in an introductory course, we first have to focus on the foundations. There are lots of other interesting things. For example, a plume filter. A plume filter is a very interesting probabilistic data structure. And you can store, or it stores a set of numbers. And it can tell you with a probability if a number is in or not. Concretely, false negatives are not possible, but false positives are possible. But it's a super efficient data structure to tell you whether you have a data point in a set or not. And in fact, because false possible matches are possible, and false negatives are not. The Bloom filter could tell you something like, is possibly in the set or is definitely not in the set. And you're wondering, what is this useful for? For example, in stream processing or for caching in certain cases, such a data structure can be super helpful if you have a huge stream of data and it's just too inefficient to look this up in a tree or in a hash table. Then you would be using a Bloom filter. It's probabilistic, so it may have some error, but this is something you can study on your own if you wish and see how it works, but it's obviously not relevant to this course. The union find data structure is also something that is quite interesting. It stores a collection of disjoint or non-overlapping sets in a very efficient way. And what is also something that is extremely interesting, but again, extremely complex and takes quite a lot of time to discuss, so we're not able to do it in the introductory course, is to find the kth largest element in an unordered sequence. We have seen how to find the largest data set, like the largest entry in a data set. You would just go through from left to right and always check if the next one is greater than the one before. And this is how you would find the largest one. You can obviously do this in O of n. If you find the largest one, if you want to find the largest one, you could also sort the data set, but the complexity is O of n log n, so more than O of n. If you want to find the second largest data set, you can obviously sort and pick the second largest one or the third largest or the kth largest. But if you don't want to sort, but still efficiently find the kth largest, this looks quite tricky. Say, we've just seen that in O of n, we can find the largest one. The second largest one, we could also find in O of n, because we can go through our data set and just keep two helper variables to store the largest and the second largest. We could do the same one with the third and fifth largest. But the larger k and fixed, the more helper variables you need. And it turns out if k is actually a variable, and you want to find the kth, which is varying, the kth largest element in an unordered sequence, you can do this in O of n with a certain trick. And that algorithm is called the median of medians. So you don't need to sort the data set, but you can find the k largest element in an unordered sequence. And k is varying. So just building all these helper variables is not the right approach to do it. And there's a specific algorithm to do this. So I hope maybe this outlook gave you some insights, what you may wish to study during the summer break or something, in case you have time. The string matching is the mandatory problem, and a few words also on the coursework. So you know the submission deadline for the mandatory and the exam bonus problem is June 29th, so the end of the June 29th via Primus. I will check all your submissions at once in batch, and then I'll give you feedback. In case there is some major problem, you will have a few days to correct this, but this happens quite rarely because these problems here are very freely posed, so you have lots of freedom in implementing them. And if you have any questions about the coursework, because you still have a little bit more than 3 weeks to submit, let me know. And I'll be happy to give feedback. Don't be late, there will not be any extensions. And once you submit in Primus, please check, sorry, not Primus, iLearn. Please check that you have really submitted it, because sometimes there are students, they claim they have submitted it, they didn't notice the submission didn't work. This is something that just creates unnecessary difficulties for everyone. So always after you've clicked submit, and it's submitted in iLearn, please check that it's really submitted and that the submission went through. These are the selected algorithms, and there's obviously some coursework on selected algorithms. There is coursework on the Strassen algorithm. There are 2 problems. Here we are actually looking at naive matrix multiplication and the Strassen algorithm in terms of recurrence relations. And for these recurrence relations, you have to find the worst case running time complexity. You can either manually solve them, or you can try to use some other tool we have discussed in order to solve these recurrence relations. There is also some problems on the fast inverse square root. So here the Newton method, and then the bit manipulation if you wish. There are other problems in here about algorithms we have not discussed. However, there are some problems starting problem 14.3 up to 14 dot whatever, up to 14.8 or something, which also address matrix multiplication. But in fact, if you multiply multiple matrices together in order to do this in an efficient sequence, this is some theory we have not discussed in the course. It will not be really relevant towards the exam this year. So when you have multiple matrices that you want to multiply with each other and you want to do this efficiently, so this will not be relevant, or it's not required towards the exam that you do these problems. However, if you have some time left at the end of the term and you want to understand bigger problems around matrix multiplications, especially if you have a sequence of matrices you want to multiply together and you want to do this in an efficient way, there are some problems here. But this is just like an expert chapter for those who really wish to become experts in this. Next week, there will be a lecture on quantum computing, and then we're also done with the content of the course, because then we've had enough lectures, and since we've taken advantage of some of the holidays or the lecture-free days, we're finishing a bit earlier with the lectures. And at the end of the term, we'll still have a discussion of last year's exam, but you have seen all these notifications in iLearn, and we still have a couple of weeks of lab sessions. And now that the flood is slowly going down, we will also be able to meet on campus again next week. Are there any questions from your side? If there are questions, maybe just raise your hand here in Zoom that I can see if you're fine. So again, there was a question here. If 14.1 and 14.2 plus 11 and 12 are sufficient, yes, because there are some here like about random number generation or prime numbers, which we didn't discuss, and all these other problems around the sequence of matrices to be multiplied. This is just more like an outlook. It's not relevant. But if you want to learn something, give a try at it. So I didn't see any other questions. So we're done for today. And I wish you a good weekend, and I hope to see you back on campus next week now that the flood is gone or slowly going down, and we'll be able to meet in a lab again after we did the lab sessions online today. So take care. Bye-bye.